Video lesson 11.6. So a lot of times with these types of functions, you have to interpret the information or the data that's going along with it. So we call these like graphing stories. There's information within the question, within the graph itself, and it kind of gives a little bit of a story and a depiction of what's happening as you kind of go. So we'll go through some of these just to kind of get a brief understanding of it, and then I'll let you guys utilize some practice problems for to make sure you understand what you're doing. All right, so let's look at number one. So John left his home and walked 3 blocks to his school, as shown in the accompanying graph. So what is one possible interpretation of the section of the graph from B to C? So we're specifically talking, let me highlight that here, from B to C, which is this portion right here. So notice the characteristics of that part of the graph. That's a flat horizontal line, and because of that, there is no, there's a change in the X, but there's no change in the Y. So there's no, in this case, the Y part is the distance from his house. So he's not going anywhere, right? From B to C. The time has increased, right? Because we went from B to C. If I was to kind of do this, right? So the time changed, but here he hasn't moved, so to speak, right? With that part. So in this case, based on these questions, I want to look for something that indicates that he hasn't moved. Time has changed, but he hasn't moved in his location. And if I read through these, right, these answer choices, I see that number 2 says that John waited before crossing a busy street. So that one here indicates that he has been waiting in time, but no, he hasn't physically moved. For this one. So that's the kind of questions that sometimes come out of these, and you have to interpret it based on the context of the question. And the key part to that is within the context. So like here, I've got time, and in this case, the distance over here. So it all has to make sense with respect to your X and Y and what you're referring to. All right, look at number 2. All right, if you look at number 2, all right, it wants here. So in the graph, Mary's distance from home, which is point A, to work, which is point F, at various times during her drive. So Mary left her briefcase at home and had to return to get it. State which point represents when she turned back around to go home, and explain how you arrived to the conclusion. So based on this graph, right, I'm looking at here. Again, here's my time as my X and the distance from home. So in this case, she started home, she traveled some amount of time and some distance, right? Then this part here, at B, it's indicating that she's going essentially backwards, right? Her distance away from home is going down. So this portion here says that she went back home. So B, right, represents, B is the point that shows, oh, sorry, it's Marie, not Mary. Marie turned around to go back home, right? So, because in this case, that positive increase, right, represents her going away from work, from home. And if it was a negative, in this case, or a downward or decreasing slope, that shows that we are going back towards the house. All right, Marie also had to wait at the railroad track for a train to pass. How long did she wait? So again, we're looking for a wait, right? If she's waiting for it, that means she is not moving. Time is changing, but her distance is not. So I'm looking for a flat part of the curve of the function here. In that case, that's D to E. So from D to E is when Marie waited for the train to pass. So again, looking at the other parts of the graph, right, you can see here some just interpretational things, like from C to D and E to F, she's going away, right? She's getting further away from her home, right? And the slope indicates the speed upon which she did it. Here, right, it's not as steep of a slope, so Yoshi's going further away, right? It's not as fast of a time. Here, she's traveled, from 0 to approximately, let's just call that 6 or 7 miles, right? She did that in a span of 15 minutes. Here, she went from that, whatever it is, like I said, 6 or 7 miles spot to 20 miles, right? So she's covered a significantly more distance, but in a less time. She only did that in 10 minutes. So that's the slope here represents that. So the steeper the slope, right, the faster, in this case, the faster she is driving away from home. All right, let's look at one more of these types of examples. And this last one here represents a jogger's speed during her 20-minute jog. So we want to know which statement best describes what a jogger was doing during 9 to 12-minute interval of her jog. So from 9 to 12, so let's highlight that part first. So 9 is here to 12 is here, right? So again, that's a flat part. So she has a constant rate, right? She's just consistently, time is changing, but the speed is not, right? So the question is she waiting, right? Well, she's not waiting around. She's not standing still, which is what you might want to look at, and which is why choice 1 is there, because that would be similar to what we did in the previous questions. But in this case, our y is the speed, right? Is speed here. So this number doesn't represent the difference in her distance away from something. It's how fast she's going. So from 9 to 12 minutes, she's still running that entire time. She's just running at a speed of 6 miles per hour constantly. So that's a constant rate of change, which indicates number 4. So that's how the interpretation has got to be very careful. You really got to make sure you pay attention to the details of what the X and the Y axis represent, because based on what they are can determine what type of information you are applying to these types of questions. So do be extra careful about that. That to me is the tricky part. You have to just be mindful and observe everything going on in the context. All right, example number 4. Let's actually graph one of these out a little bit based on what they tell me. So in this first scenario, let's see here. We got driver leaves home from a business trip and drives at a constant speed of 60 miles per hour for 2 hours. So that means they start at 0, right? So they're taking off, right, from home for a business trip. So they're starting there at a constant speed of 60 miles per hour for 2 hours. So they start at 0, 0, right? They start at 0, 0 because that's quote unquote home. Right, and then they're traveling for 60 miles for 2 hours. So the x-axis is your hours, your y-axis is your distance. So if our time here is 2 hours, so we're going to call 2 for the x-axis and 60 for the y-axis. So that's going to be a point of 2 comma 1 comma 60. Sorry, not 2. 1 comma 60, because we're going at it's 60 miles per hour, right? So we got 1 to 60, and that means 2 would be another 60, which would be 120. So overall, right, we're going from 0 to 1 comma 60 and then 2 comma 120. That would represent that portion of the change, because it's 60 miles per hour. So first hour is 60, second hour is another 60, which would be the 120. All right, so that's this part. I'm just gonna use my straight edge here and draw a line. All right, so the next part says her car gets a flat and she spends 30 minutes changing it. So she spends 30 minutes changing that tire. So in that time, right, so you've got 30 minutes, so that's, in this case, 1 box. Right, because my boxes go by half hours. The distance does not change. So that's going to be a flat part or a horizontal line here. So we're going from 2 to 2.5, right? That's going to be this part here. From here to here. All right, I'll do that part here. There we go. With my straight edge. All right. And then she resumes driving and drives 30 miles per hour. So now she's driving at a different rate. I'll do it in a different color here so it's easier to see. All right, she's driving at 30 miles per hour for the remaining hour. So again, so we have that block. So now we're going from the 2.5 spot, right? So 2.5. She's traveling 30 miles an hour, right? So she's going from here, excuse me, every 30 miles in 1 hour. So from here to here, right, is my spots. So I'm going from here to here. So I'm going 30 miles. So I'm going to increase. That's 150. So that would be here to here, right? Because she's increasing from here. She's going from here to here. That's plus 30. So you're at the 2.5, oops, I'm sorry, comma 120, that's where we started. And then we're adding, so we're going another hour's worth of time, 3.5, and we're adding the 30. Let me do it down here so it makes a little bit more sense. We're adding the 30 to this number, 150. So that's how I got this part, and this would be my line that represents that portion of the graph. So again, the hard part about these is interpreting and being specific in the information as you go through it. With those things, I think I like to plot out the points as I go. And you can even write notes. Like I can say like here, I can be like, 60 miles per hour. And then this part was 30 miles per hour. You know what I mean? Like I can jot down like the specifics in the notes, right? That goes along with it. There's in this portion in the middle here that we had that flat part, right? Which I did in green, right? So this part here, that's like this empty space, right? There's a weight, right? There's a weight there because she's fixing the tire. So there's no distance, right? So again, just however helps you, interpret the information so you can graph them. That's the important part, all right? Being able to just interpret the information and then graph it accordingly. All right, one last thing, and then we'll call it a day for this lesson, and that is there's a specific type of piecewise function, and that is sometimes important to be able to see, and that is what we refer to as step functions, or a lot of students call them staircase functions because they look like a staircase. But these step functions are really like a specific type of piecewise function. The most common or most famous one is referred to as the greatest integer function, right? Which has that special notation, which if you can see over here, they use these hard brackets for. If you look up at the graph here, here's a good example where y equals, and it got x. So this is saying y equals the greatest integer of x. So what that is inferring to is that you're looking for the largest integer less than or equal to whatever that x value is. So, from here, something to the effect of, for example, if you say like anything between -2 and -1, right? All of those values end up giving me an answer of -2, right? Everything from, in this case, 0 to 1 is 0. So even if I got like 0.5, the relationship to it its y ends up being 0. Like if I give you like 1.75, right, the answer is going to kick out just a number, in this case the large number less than it, which would be 1. So that's the kind of thing there. These are really common when dealing with like conditional statements that have to be like like within terms of ages and stuff like that, and the amount of people, like where they can interact inside certain types of games or leagues or stuff like that. Any of you who have participated in any type of like little league, there's always some type of an age cutoff, and it's the same for each level. So it would be like, like from like 5 to 6 can play in this level, and then 6 to 7 can play in this level. So it doesn't matter where you are in that age bracket, you would be, you get put into that group. Just because you might be like, 6 years old and like 9 months, doesn't change that versus someone who's six years old in 1 month. You would all kind of land into the 6-year-olds, you know what I mean, kind of a group. So that's kind of how it works, right? So these kinds of examples, you'll see them as the graphs here, like I said, on the side, with these kind of this stepping kind of a function. The other thing you could do is they could say, like, what is this? So like this would be the way it would look symbolically. So what is the largest integer less than or equal to 2? In that case, it's just 2. What's the largest integer less than or equal to 1.5? That would be 1. So again, I didn't get up to 2 or anything in there, so it defaults back to 1. And then this one would be -3. So like even if I had like the greatest integer of negative like 3.999, right? It based on this information, that would land me in -3 because I'm still within that -3 group, so to speak. All right. So that's kind of how that works. Okay. Let's just do one little quick one, and then, like I said, we'll call it for a day here. But I just going to have it, just kind of plot them a little bit so you can see what I'm talking about. Nixkin started playing basketball game at the age of 4 in Group 1. He remains in the group until his next birthday, when he is required to move up to the next level. So we want to draw a graph that represents this information. So at 4, right, he starts in Group 1. So at 4, right here, he starts in Group 1. Now he's going to be in Group 1 all the way until he turns 5. So, but we have an open circle for 5 because when he actually gets to 5 years old, right? Oh, that kind of keeps looking like a solid circle. All right, there we go. When he actually reaches 5 years old, he automatically bumps up to the next group, which in this case would be Group 2. Again, his entire time that he's 5, he'd be in this group until he turns 6. So open circle at 6, because at 6, the second he turns 6, he gets bumped up into the next group, so on and so forth. So open circle at 7, right? Open circle at 8, open circle at 9, in which he would be bumped up to group 6, and obviously it would continue on for whatever that next portion would be. So that's the interpretation. That's the part there that has to go. He's going there, and he would be continuing in this fashion. This question just simply says until he finishes in Group 5, so we're done at 5. But that's the process. That's the key to these step functions, all right? I really just want you to see them, have an understanding of what they look like, the understanding the interpretation, because they are a unique asset of the piecewise functions. So, all right, so take an opportunity, again, make sure you copy down notes, make sure you try all of these things, and then utilize this to help you with the practice problems moving forward.